So we've been using this little arrow to visualize the relative wind. Our idea is basically imagine that you're a pilot in this airplane and imagine that you can actually see this arrow physically and that it moves with the wind. What would you see? So the instrument we've come up with is this. So here we are in cruising flight. The wind is coming from more or less straight ahead and it's really plump because we're going really fast. Now let's say we start slowing down. Let's say we're preparing for landing. Here we are. Now the airplane is pitching up relative to the wind, and the wind is getting weaker and weaker. You can see that the ball is getting smaller because the wind is weaker, and that corresponds to the analogy that the arrow is farther away from you. And the arrow is also pointed from below you more than before. And eventually, if you get to the red area down at the bottom of the display, this is where you expect your wings to stall. This is where you do not want to be.
All right, so back up a little bit. What is this, and what does it have to do with this? Because it looks like they're kind of moving in the same way.
Well, so this arrow is a visualization of the arrow of the wind, if you will. This is the wind blowing at you if you were sitting in the airplane thinking about the wind as it passes by you. Mm-hmm. And this instrument is what you would see sitting in the airplane.
So what is this instrument?
So this is called Airball. This is the Airball instrument, and this is what we have developed over several years to try and build a better way for pilots to fly their airplanes more safely.
Okay, and what are all these little bits that I'm seeing?
There are various bits around that tell you where you want to keep this wind arrow for various phases of flight, right? So one of them would be the best rate of climb, the other would be best angle of climb, and various other points that are known to pilots. Mm-hmm. But in general, without all of these little divots, all you need to know is that the strength of the wind is related to the size of the ball. Big ball, strong wind, small ball, weak wind. Mm-hmm. And the ball shows you where the wind is coming from. So if the wind is coming from below, so-called high angle of attack, then the ball goes below. Mm-hmm. And notice that we're not really showing too many numbers here. We're showing you your speed through the air just as a way to try and link it to the way people fly today. But ideally, we don't want any numbers here at all. We just want you to think of it as an air surfing experience, right?
And so what is this little thing down here?
The red part is where we expect that your wing will stall. So if you're going really fast, like this, mm-hmm. right, your wind is coming from straight ahead, mm-hmm. and then you slow down, and as you slow down, your wind starts coming from lower and lower and lower. Eventually, at some point, you're going to stall. And that's because of the angle that your wind is making with your wings. Even if you're flying level, notice the angle of the airplane relative to the wind. Mm-hmm. And that's when the wind will drop, and you'll do this, and you'll pick up speed, and then you'll go back up. Yaw is also shown here. So if the wind is coming from the left, the ball moves left. If the wind is coming from the right, the ball moves right. And pilots today are used to having a little spirit level in their cockpit that tells them about yaw. It doesn't actually show them the exact yaw, but it shows them kind of something related to yaw, and they call it the ball. And the sense of the airball, in other words, if you're yawed to the left, the wind is coming from the right, the ball is on the right, the sense of that works the same way as the spirit level that people are used to using, or the so-called inclinometer that people are used to using in their cockpits. So they don't need to learn anything new. But this tells them basically the yaw, which remember is important for determining if you're going to stall or spin, the angle of attack, and the strength of the wind, or so-called indicated airspeed, or what aerodynamicists would call dynamic pressure. Now there's one more thing that this displays, which is a little bit of a technical issue, but I think it's worth talking about, which is the higher you go, the less dense the air is. There are fewer air molecules. And so in order to get the same oomph for lift producing, you're going to have to go faster. And so remember, this white ball here shows you the oomph of the air, basically how hard it's blowing. But if we model here using these little electronics, and you can see that we're displaying the height of the airplane here. So we started out at 400 feet. We're going to turn the knob here and pretend like the airplane is flying at, let's use something like 16,000 feet, 400 or something.
So this is like taking off from Tahoe or something?
Well, actually way higher than taking off from Tahoe, maybe flying over the mountains.
Okay.
Notice, in order to get the same oomph, we need to be going much faster. And so what we display here is this magenta ring that is the size of the actual speed of the airplane through the air, as well as the white dot, which is the oomph of the air. Mm-hmm. So the white dot is sized to the so-called indicated airspeed, and a pilot would call the magenta ring size their true airspeed.
Okay.
And as you see this magenta ring start increasing beyond your white ball, this tells you that you are now in a situation where you're actually going faster than you think. And this is what gets people really into trouble when they're taking off or landing from Tahoe, because as you pointed out, if you're taking off from Tahoe and you normally take off at like 75 miles an hour, well, you might have to accelerate to 85 or 90 miles an hour to take off at Tahoe. And that takes longer. And eventually, when you start climbing, your airplane is going to make less power. And so having that piece of data, which pilots refer to as their density altitude, visualized in this really easy way, is another important part of this instrument. And we can, again, put all of that in one single thing that you can glance at, and it just tells you everything you need to know. So what we've shown you is the display. And we also have this little demo device here that, as I move this arrow around, it sends signals to this device telling it, where to move the little blob. But really the key is that we can have something that measures the relative wind directly and sends the appropriate signal. And this is the other part of our project, which is the probe. Now, this doesn't use any new physics. This physics that this uses has been known for, ages. Basically, it is a curved ball shape with a series of holes on it that sniff the pressure of the air. And these feed into little electronic pressure measuring devices that then send this information using a battery-powered wireless link to the display. And the idea is that this can be clipped to the outside of an airplane, for example, for flight instruction, or just if you're curious, or if you're flying with it just for fun. And it gives you all the information you need to know to paint this display we have created here.
Or for safety, I take it.
Or for safety, absolutely. Of course, we imagine that once this becomes popular, there will be versions of this which can be integrated directly into an airplane. You can buy it from some big manufacturer like Garmin or whomever. But in this phase, where we're just trying to produce something to convince people that this is an interesting approach, our best way of doing it is to make something you can clip to your airplane without having to go through the regulatory process of integrating something directly into your plane. Mm-hmm. And then, of course, there's the intermediate case of experimental airplanes who are allowed to add more experimental things to their airplanes, and we hope to make versions of this probe that people with experimental planes can put on their airplanes more permanently.
So how do you attach it to your plane?
This attaches to one's airplane using a little temporary clip that attaches to the strut of the airplane. It works very well for Cessnas. It works well for an airplane where you have a tie-down mount where you can clip this to the bottom of the wing. Basically, anywhere you can come up with a temporary clip that the feds will recognize can come on and off without tools, you can put this on. Now, we have created various mounting systems of our own, but you could invent pretty much anything. We will show here, for example, one of these mounting systems, if I can dig it out of the cupboard. Sorry. Right. This is an early prototype of a mount we made for a Cessna. So this clips onto the strut of the airplane, and a bunch of straps go around here to hold it in place, and then we use ram mount devices attach. Sorry about this rummaging. I wonder if we have any ram mount arms.
Maybe it's on your airplane.
Say again?
Maybe it's on your airplane.
It might indeed be on the airplane. Well, what we've standardized on is
Is it kind of like this?
It is like this. That's another example of one of those, right? We have different shapes for different airplanes, and we're experimenting with different things. But basically, using these kinds of arms that are made by Ram, we can attach anything to the strut of an airplane and attach a clip that attaches this, and it can be clipped on and off. Ram actually makes this very, very useful little snap-on, snap-off clip, which I'm not sure if we have any here.
That's all right.
I think it's on the airplane. But yeah, in any case, that's the that's how it's made.
All right, so this ball
Yes.
that I would see on the display,
Yep.
do you have any metaphors for like what that would mean? Or should we save that for another chapter?
Well, the metaphor is basically that it is the arrow of the relative wind.
Mm-hmm.
That is basically the metaphor.
Yeah, I kind of like the idea also of thinking of it as a windsock, right? Is it kind of like a windsock?
Well, it is in some ways a windsock in the sense that, and this is one of the key things about our device, there are a lot of similar devices that display information in sort of a data visualization way. So you have a little number, or you have a little dial, or you have a little bar chart. But the whole point is that this, in conjunction with the fact that we actually update the display at 20 times a second, means that if you're in turbulence, you will see the ball moving around like this, and you will very, very, very clearly see things about the airflow that you would not normally see with the normal airplane instruments.
Mm-hmm.
And so in some sense, its motion acts as this very physically linked windsock that tells you things about your flight that normally you wouldn't know from a regular instrument.
Mm-hmm.
And it's also, in that sense, a windsock because it is very physically linked to the direction that the air is coming from. You can look at it and immediately tell what the direction and strength are.
Mm-hmm.
So in a sense, this is a digital windsock.
Well, I think it looks awesome. What if I were to want one for my airplane? Where would I get it?
So what we're doing is we're trying to miniaturize this probe right here, and also in some ways miniaturize this display, so that for under $500 in parts, we can produce a complete kit of probe plus display for someone to be able to try out in their airplane. Our work is all open source. Our designs are all out on the internet for all to see. Our code is on the internet, and we have a blog where we talk about everything we do, the good and the bad and the ugly. You know everything we do as soon as we know it.
Can you write down your address?
Of course, yes.
And also maybe show us your 3D printer.
I will. So the address to go to is airball.aero. Airball.aero.
And what gave you this idea of starting up Airball?
So the idea first came from the unfortunate crash of a 777 at San Francisco Airport back in, I believe it was 2013. That was caused by the pilots losing track of their speed and angle of attack and getting too slow and too low and not being able to recover quickly enough. And I tried to think about what kind of instrument would make it easier for me in my kind of flying to not get into that situation. And after going through a whole bunch of false starts and thinking about various scenarios, I came up with this airball visualization that has remained stable as of maybe a year or two into the project. I think we kind of narrowed down on just this being the visualization that worked out for us.
Mm-hmm.
And of course, all of this work is done thanks to my 3D printing. Much of this, all of these parts are 3D printed. what you see here is, this is my workhorse 3D printer, and this is another one that needs some maintenance right now. This 3D printer is a very interesting one. It's made by Prusa, and it is actually open source. You can download the designs online. You buy it as a kit and you put it together yourself. And a lot of the parts that you get in order to build this 3D printer are themselves actually 3D printed. And there are a lot of fascinating little things to learn as you put it together. For example, how you can put together 3D printed parts using zip ties. Because when you 3D print something, you can put little channels into it that you could not possibly have carved out with any tool. And you can get a zip tie to zip through that and turn around and hold two parts together in this very clever way.
So that's how you got the little things for measuring the wind, right, in your probe, in the nose of your probe.
That's right. These are all 3D printed, and they would be really expensive and time-consuming to make out of metal, for example. But with 3D printing, it's much easier because you can make the little channels in one piece.
And so at the time when you first developed this, you were working with Android, right?
Yes.
And then you tried it on Google Glass?
Yes, I did. So the Android app was a little bit slow, although maybe we were just using a slow phone. But more importantly, the Android version has all the problems that that putting a flight instrument on a commodity phone has, right? It is, you'll get chats, you'll get text messages, you'll get little notifications. It's a very noisy interface, and also the screen is not really all that bright.
Mm-hmm.
We tried it in Google Glass, but unfortunately in a cockpit of an airplane you need something super, super bright in order to stand out against the background. So what we decided was that we needed a custom display that is very compact, but also super, super bright. And what we've ended up with is a prototype of a display that is, technically it is 1,000 nits or 1,000 candelas per meter squared, which is basically sunlight readable.
And then what was the story with the EAA contest?
Well, so at some point after tootling around with this a little bit, I decided, I found out about the EAA's Founders Innovation Award in 2016. And I really did not know if anyone would take this work seriously, but I applied anyway. And so here I was one of the finalists, which was like, oh, great, fine. I went there, I presented my stuff, and I waited in apprehension, and they started calling out, here's the 5th place, and someone else.
At Oshkosh.
And here's the 4th place, and that was in Oshkosh 2016. And here's the 2nd place, and it was someone else, and I was the only person left, and I was like, oh my God, really? So then it turns out in 2016 I did indeed win 1st place, and here's my little trophy that I got.
Oh yeah.
And so since then I've been working on this, trying to improve it, and in the process I actually started a flying club in order to gain access to an experimental airplane called the Coyote Valley Sport Flyers. And so now I have a plane on which to test this, and I'm developing it more and more.
And soon you'll be looking for more people and more flight instructors to test it. So
that is actually the key, right? The key is to determine the ergonomics of how, both the ergonomics and the sort of curriculum for how this gets used in flight instruction. Because my hope is that, pilots have to get a flight review every 2 years. So flight reviews and primary instruction are a good way to catch pilots and give them these new skills and send them out into the world. The question will be, how can we make something that you can slap into your average Cessna conveniently and be able to use without too much trouble, either from a regulatory standpoint, because you can't bolt and screw and rivet stuff into a Cessna without talking into the feds, but also you don't want it to be so inconvenient that someone has to do several things just to get that thing ready for a flight. So our best bet right now is a display that attaches to the cigarette lighter adapter and is really bright and connects wirelessly to our probe. And the probe, we hope, well, the current version of the probe has about a 12 or 13 hour battery life. So you can just charge it in the beginning of the day, slap it on the airplane, and just fly all day, and take it off at the end of the day and put it on the charger. So we hope to work with more flight instructors to get more feedback on the ergonomics, like how big of a screen do you want, what is too big and what is too small, where would you mount it, how would you use it, how would you teach other instructors how to use it. This is all uncharted territory, but we've had very, very positive feedback from flight instructors in general, especially those who like to use relative wind as the metaphor for teaching.
All right. Any last thoughts?
Yeah, I guess I would say that a lot of the thoughts that underlie the Airball project come from this book that was written in 1944 called Stick and Rudder. And so I just recommend anyone who's interested in this to go ahead and read Stick and Rudder. It's available actually online for free now because the copyright has expired. And it's beautifully written and really describes the phenomenon of flight in correct physics but without using numbers in a manner that anyone can understand.
And really, then that's what Airball is trying to get people to visualize in their airplane, right?
Exactly.
So that
Yep.
it's a whole paradigm change of how we fly.
If we are successful, then we are building the instrument that Wolfgang Languish, the author of Stick and Rudder, would have built had he, in 1944, the technology that we have today.
All right. Well, thank you.
Thank you very much.